Welcome to the class of stochastic processes. The transition probability function Pijt. For any ij, we define Qij as Vi times Pij, where Vi is the rate at which the process makes a transition when in state I, and Qij is the rate when in state I at which the process makes a transition into state J. So the destination has to be J, but here Vi can be any transition to anywhere. The quantity Qij are called the instantaneous transition rates, and Pij is the probability that the transition is into state J. So obviously, we know Vi is equal to summation Vi times Pij, and we sum over all possible J. And that is summation Qij, summing over all possible J. And Pij is equal to Qij over Vi, and is equal to Qij over summation Qij. So we have the following lemma. A. Limit h goes to infinity. 1 minus Pii h over h is equal to Vi. And why is that? Remember, in the Poisson process, we say the probability that we have one arrival is equal to lambda times the time period h plus little o of h. So that means if we move the h over the left-hand side, so we have probability over the period time h, and that will be equal to the frequency lambda, right? So here we have the same idea. 1 minus Pii h, then because Pii h means the process starts from I, and after h period time, the process is still going to stay at I. Okay, so 1 minus Pii h is the probability that starting from I, after a period of time h, the process is not at the state I, right? So divided by h, that would be the so-called frequency here is Vi. Okay, so the Vi has a very similar nature as the lambda in here. Okay, and the second lemma is limit h goes to 0, Pij divided by h is equal to Qij. So Qij refers to rate too, right? But with only one difference is that starting from I, the destination has to be J. Okay? Conqueror equations for s and t greater than or equal to 0, Pijt plus s is equal to summation Pik t times pkjs, and we sum over all k, so k from 0 to infinity. And this is just like the discrete version, like Pijn plus n is equal to summation Pikn times pkjn, and we sum over k from 0 to infinity. So with this Chapman-Conqueror equation, and we can derive the following Conqueror backward equations. So Pijh plus t minus Pijt, and Pijh plus t can be written as summation Pikh times pkjt, and we sum over all possible k, right? And minus Pijt. So this is from Chapman-Conqueror equations. Okay? Then we can single out Pih and Pijt from here. So basically we single out. So this will be equal to this, and plus Pih times Pijt. So basically we single out this spatial item, and then we make sure k is equal to I, because we single out this item. Okay, so we have summation Pikh times Pkjt minus 1 minus Pih and then times Pijt. Then we divide it by h on the both sides. So divided by h, then we let h goes to 0. Okay, so the left hand side will be like this, and the right hand side divided by h and let h goes to 0 will be like this. And if we look at the left hand side, this is actually the gradient function or derivative function of the transition probability function. So we call it Pij prime of t. And that is equal to summation Qik. Okay, so this is Qik. By definition, this is Qik, and we have a summation in front, right? And times Pkjt minus, and this by definition is Vi, right? Times Pijt. So this is the Conqueror backward equations. And based on that, we can look at the pure burst process and write down the Conqueror backward equation. And recall that pure burst process means that we don't have that in the process, right? So, and also pure burst process is actually Poisson process. And let me write down the Conqueror backward equation again. So we have Pij prime of t, and that is equal to summation k is not equal to I, then Qik Pkjt minus Vi times Pijt. Okay, now so we have pure burst process. So the left hand side is Pij prime of t, and the right hand side, look at this, because this is pure burst process, right? So starting from I, and there's the next transition must be I plus 1, right? So Qik, and from I to I plus 1 will be lambda I, right? So Qik will be lambda I times Pi plus 1, because the only possible k here is I plus 1. Okay, so times Pi plus 1 Jt minus, how about the Vi? Vi is the overall transition rate, but because this is a pure burst process, so the overall transition rate is still lambda I times Pijt. And similarly, you can derive the P0J prime of t like this, and also Pij prime of t. Okay, so if you look at this Pij prime of t, this is the birth and death process. So from I, you can go to I plus 1 or I minus 1, because this is birth and death process, right? So I can go to I plus 1 or I minus 1 with rate lambda I, right? And mu I. So basically, the Qik from I to I plus 1 will be lambda I here, right? And plus mu I, right? So mu I is from I to I minus 1, like this. And minus the overall transition rate, that is lambda I plus mu I, okay? Times Pijt. Another example. Consider a machine that works for an exponential amount of time, having mean 1 over lambda before breaking down. And suppose that it takes an exponential amount of time, having mean 1 over mu, to repair the machine. If the machine is in working condition at time 0, then what is the probability that it will be working at time t is equal to 10? So we can define state 0 as when machine is working, and state 1 is when machine is being repaired. Okay, so this is 0 and 1. So obviously, when machine is working, and the rate that it would make a transition to 1 will be lambda, and 1 to 0, and that is the time, the average, the rate will be 1 to 0 will be mu, right? That is associated with the repair time, right? And we know that the repair time has the mean 1 over mu. So obviously the rate would be mu. Okay? So we can derive the Conqueror backward equation like this. P00 prime t will be equal to lambda times P10t minus lambda P00t. Okay? And we can derive the P10 prime of T2. Okay? So we have this equation and this equation. And for the first equation, we can multiply by mu on both sides. And for the second equation, we can multiply by lambda on both sides. Okay? And we can sum these two equations and we get mu P00 prime t plus lambda P10 prime t. And that is equal to 0. And if we take integration on both sides with respect to t, we get mu P00t plus lambda P10t equal to c. Okay? And we know that P000 is equal to 1 because P000 means starting from 0. The machine after 0 time is going to be still at state 0, and obviously that will be for sure, right? So that probability is 1. And starting from state 1, after 0 time, the machine or the process is going to be at state 0. This is impossible, right? So the probability would be 0. With these two boundary conditions, and we plug in this equation, and we get c is equal to mu. So it turns out that we get lambda P10t is equal to mu times 1 minus P00t. Okay, so with lambda P10t, we can plug it into this equation. So lambda P10t will be substituted by this, and turns out that we can solve for P00 prime t, and that is equal to mu minus mu plus lambda times P00t. Okay? And obviously this is a differential equation, and so we can solve for this differential equation, and we get P00t, and I'm going to skip this part, okay? And the result, P00t will be like this. But the question is asking, what will be the probability that it will be working at time 10, right? So it will be working, so 0 to 0, because state 0 means the machine is still working. So P0010, you just plug in 10 in here, okay? And you get the result. Similarly, we can talk about the Conqueror forward equations. Okay, so forward equations Pij t plus h minus Pij t, and that is so this can be written as summation Pikt Pkjh, and summation k from 0 to infinity. This is based on Chapman-Conqueror equations, right? Okay, minus Pijt. And now we can single out Pjjh and Pijt from this. Okay, so we get summation Pikt Pkjh, and notice that k is not equal to j because we single out this item in the back. Okay, so we have summation Pikt Pkjh, and summation k is not equal to j, minus 1 minus Pjjh, and then times Pijt. And similarly, we can divide it by h, and that h goes to 0 on both sides. Okay, so on both sides, and it turns out that the left hand side, this is the Pij prime of t, and the right hand side, this is Qkj, right? Because by definition, and this is Vj, okay? So we get the Conqueror's forward equation. So we have a theorem that summarizes the result. So under suitable regularity conditions, we get this Conqueror forward equation. And there are a few examples that you can write down the Pij prime of t. I think we should put t here. Okay, and I'm going to leave this as examples for you to practice. So you can write down the pure burst process, and you write down the Conqueror forward equation. Okay, and also Pij prime of t, Pij prime of t. Okay. Limiting probabilities. Remember that in the discrete version, Markov chain, we have limit n goes to infinity Pij for discrete version, and we know this is Pij, right? And similarly, in the continuous version, we use Pijt. That means starting from I, after a period of time t, the process is going to be at state j. Okay, and then this limit probability is defined as Pj. We use its notation. So basically, Pj, we ignore where the process starts from, I. Okay, so there's no I in here. Okay, so just like this, right? Pij has nothing to do with I. That is where the process starts from, right? Okay, so this is called limiting probability. And actually, the interpretation of this Pj is the long run proportion of time that the process is in state j. So if we use Conqueror forward equations, Pij prime of t is like this, and we let t goes to infinity on both sides. Okay, so it turns out we will have the limit t goes to infinity, Pij prime of t, and then limit t goes to infinity, so this will be pk, right? Because let me say this again. We ignore where the process comes from, so there will be no I in here. Okay, and limit t goes to infinity, this will be pj, right? Now, the left hand side, limit t goes to infinity, Pij prime of t must be 0. Okay, so here, this must be 0. Why is that? Because we know that Pijt is a bounded function. Recall that Pijt denote the probability. So probability must be within 0 and 1 in this range, right? So think about this. If Pij t goes to infinity, Pij prime of t is equal to some constant that is greater than 0 instead of 0. And this must mean Pij t goes to infinity when t goes to infinity, right? Because the gradient is some constant, remains some constant that is greater than 0. So basically the function will keep growing, right? And goes to infinity. But that is not possible because Pijt means probability. That must be restricted within 0 and 1. So if this is the case, that means limit t goes to infinity, Pij prime of t must be 0 instead of some c that is greater than 0, because this is not possible. Okay, simply because Pijt is a bounded function. So Pij prime of t must converge to 0 if E ever converges. Okay, so that means this equation must be, the left hand side must be 0, and the right hand side is summation qkj pk minus vj right? So we can move the vj to the left hand side, so we have vj is equal to summation qkj pk, together with the fact that summation pk is equal to 1 because pj means the long run proportion of time, and that is probability. Okay, so summation pj must be 1, and we can solve for the limiting probabilities. And we have a few remarks here. So we have assumed that the limiting probability pj exists, but it does not always exist, only when the following sufficient conditions hold. Number 1, all states of the Markov chain communicate with each other. And the second, the multiple chain is positively recurrent. If these two conditions hold, then Pj will exist. Then we can solve for the limiting probabilities. Okay? So for the star equation, in the long run, the rate at which the transitions into state J occur must equal the rate at which transition out of state occur. So incoming and outgoing are equal to each other. So this is called balance equations because the processes somehow make a balance in the long run. Okay? So we mean here. So Vj Pj is equal to summation Q Kj Pk. So this is called balance equation. So for example, for the birth and death process, we can write down the balance equations. So the rate at which leave is equal to rate at which enter. So for example, birth death process, this is 0, 1, 2. And we know that 0 to 1, that is lambda 0. 1 to 2, that is lambda 1. And this is mu1. And this is mu2, right? So basically for state 0, the probability that the process is going to be at 0 is P0. So the leaving rate will be lambda 0, right? Lambda 0 times P0, okay? And that is equal to mu1 P1, right? Mu1, so from 1 to 0. So the outgoing will be equal to the incoming, right? So lambda 0 P0 is equal to mu1 P1. And for state 1, for example, lambda 0 P0 plus mu2 P2, okay, will be equal to lambda 1 P1 plus mu1 P1, right? So that will be like this. Okay, so you just draw the diagram, and you keep in mind that the incoming rate will be equal to the outgoing rate, and then you write down the balance equations, and then you can organize all these balance equations, right? So P1, for example, for this equation, you get P1 is equal to lambda 0 over mu1 times P0. And P2 will be equal to lambda 1 over mu2 P1. But you know P1 is like this, right? So you can plug in here. So you get lambda 1, lambda 0 over mu2, mu1 times P0. And you keep going, and it turns out that Pn, you can express Pn as a function of P0, right? That would be like this. Now, you just need to solve for P0, and you plug in here, you get all the Pn, right? And how can you solve for P0? Remember, we have summation Pn is equal to 1. So you can solve for P0, and you plug in the equation, you get Pn like this. Now, when will the limiting probability exist? So think about this. If the denominator is equal to infinity, then Pn must be 0. Then that means the limiting probabilities will not exist. So we want to make sure the denominator of Pn will be less than infinity, right? So that means this term has to be less than infinity. So that will be like this. So that is the condition, right? So think about the example of 6.6, that is the MMS example. So MMS means that the number of servers in the system is S. So mu1, mu2 up to mu_n. So when the number of people in the system is greater than S, then all the mu_n will be as mu, right? So summation S mu to the power of n. And the numerator will be lambda because the arrival rate is lambda. So lambda to the power of n. So this condition will be like this. And the summation from s plus 1 to infinity. Actually, this is just like you can sum from 1 to infinity. But because this is kind of like a infinite series, right? So we are only the tail terms matter. Right? So I just sum from s plus 1 to infinity. This condition is just like this condition. That means the same thing. right? If this condition holds, this condition also holds. Okay? A machine repair model. Consider a job shop that consists of n machines and one serviceman. Suppose that the amount of time each machine runs before breaking down is exponentially distributed with mean 1 over lambda. And suppose that the amount of time that it takes for the serviceman to fix the machine is exponentially distributed with mean 1 over mu. And we want to answer the following question. First, what is the average number of machines not in use? And the second, what proportion of time is each machine in use? Now, suppose we define state n means n machines are not in use. Okay? So this is the birth and death process. First, because if you have one more machine failing, one more failing machine, then process will increase by 1, right? So n to n plus 1. But if you have one machine that has done repairing, then this is considered dead, right? So n is decreased by 1, n to n minus 1, okay? So basically, here mu n, okay, that means the death. So that must be refers to the repairing time, right? And the rate would be mu. And the lambda n, that refers to the arrival. And the arrival, because we define the state as the number of machines that are not in use. So arrival will be the number of machines that are left being used, right? So totally we have n machines. And we have n machines are not in use. Totally we are left with n minus n machines that are still being used, right? So n minus n lambda when n is less than or equal to n. Okay? So based on the previous results, we can solve for P0 and we can solve for Pn. And so the average number of machines not in use will be summation nPn. Okay? So that will be like this. And to obtain the long-run proportional time that a given machine is working, and then we have to compute the equivalent limiting probability. That means the long-run proportional time that the machine is working, right? So a given machine is working, we can break down the simple space as like a conditional on n machine is not working and times the long-run proportional time that n machine is not working, that is Pn. And sum over all possible n, right? And how about this probability? When n machine is not working, this given machine is working. So so totally we have n machines, right? And when little n machine is not working, we have n minus n machine is working. Okay? And this given machine is this particular is working, is the probability must be n minus n over n. Okay? And times Pn and take summation. Revisit the shoe shine shop example. If we suppose that the potential customers arrive in accordance with the Poisson process and rate lambda, and that the service times for the two chairs are independent and have respective exponential rates of mu1 and the mu2, and we want to determine the proportional time that the process is in each state 0, 1, 2. Now we define state 0. System is empty, and 1 means the customer is in chair 1, and 2 the customer is in chair 2. Remember, this is not birthday process, as we have discussed some exercises in the class, because the birthday process just refers to the number of individuals or number of machines, number of people in the process. But here, 0, 1, 2, we need more information about that, right? Because 1 means not only one customer in the system, but the customer must be in chair 1, okay? And 2 means the customer is in chair 2, okay? Now we can write down the balance equations like this and use the fact that summation Pi is equal to 1. We can solve for P0, P1, P2, which refer to the proportional time. In the long run, the process is going to be at stage 0, stage 1, stage 2, respectively.